Madhvi started?
Yes, sir.
Okay, so let's start then. Good morning, everyone, and welcome to this technical session. On behalf of Core Committee and INYAS family, I welcome our keynote speaker and all invited speakers of this symposium. I thank Dr. Santosh Gupta for proposing this symposium on a very important theme, which is light emitting materials for societal benefit. Dr. Santosh Gupta is working as scientific officer and our new INYAS member. I now invite Chairman over.
Thank you, Dr. Rajendra, for your kind introduction, and it's been great to be part of this wonderful INYAS family. So today, on the occasion of our 7th annual general body meeting, this is a technical symposium session on the theme, a very important theme as discussed by the convener, that impact of light emitting material on solving variety of societal problems. We have a galley of speakers. We have Professor Behram from University of Oklahoma. He's assistant professor there, and he'll be speaking on new light emitting material for lighting applications, and he will touch upon some of the impact lighting material have shown in area of security. Then we'll have a very senior professor from IIT Roorkee, who is a chairperson of the Department of Chemistry. He'll be speaking on organic light emitting diode. Then we have a senior scientist from Bhabha Atomic Research Center, Dr. Vinita Grover Gupta. She'll be speaking on non-lighting applications of light emitting material and mostly discussing about the bio application side of the same. Then I'll be speaking on the aspect of how the ultraviolet light, which is not that much explored, can be of global impact in solving the current pandemic pertaining to coronavirus, and then how it can be also helpful, if time permits, also how it will be helpful if you design a material for emitting ultraviolet light for water purification technology. Then we have a speaker from IIT Ropar, who is also an INYAS member, Dr. Neha Sardana. She'll be speaking on plasmonics and metamaterial and some of their recent advancement and applications. Before further ado, I know all the audience must be very eager to listen to our speakers. I invite Professor Behram Saparov. I'll just give a very brief introduction. He is a professor at University of Oklahoma, and his expertise is on preparation of halide-based phosphor material and a development of materials for solar space application and semiconducting and magnetic properties of new chalcogenide materials. He has received several awards from, as some of them are DOE Early Career Award and NSF Career Award. Over to you, Dr. Behram.
Thank you so much. This is a new experience for me. Hi, everyone. Good morning. It is night here. So I'm not going to take a lot of time. I'm just going to go right in there because we have 25 minutes. If I go over time, please let me know somehow so that I stop. But the presentation will be on light emitting materials prepared in my laboratory. And before I go into the presentation, I just want to use this opportunity because it seems like a young scientist symposium to advertise some other projects going on in my laboratory and also at the University of Oklahoma. So in my laboratory, I currently have 3 funded projects. One of them is on the development of thin film solar materials for space applications. This project is supported by NASA here in the US. I have another big project, and this is the topic of today's presentation, on photoluminescence properties of metal halides, and this is supported by NSF. And finally, I have a project supported by US Department of Energy. This is the Career Awards. This project studies the solution chemistry of metal halides. Now, there's one thing that unites all these projects. In all of these projects, we study metal halides. And today's presentation, my presentation, will be on metal halides that have interesting light emission properties. So what's the deal with metal halides? So we have lots of papers. I'm not going to talk about all of them, just select ones that are highlighted here in yellow. I will mention, I will cite. So what's the deal with halides? Now, the audience may have heard of the terms like halides, perovskites, and related terms. So they came to the forefront about 12 years ago now. A group in Japan published a paper on using metal halide perovskite as a solar cell. And since then, this area has essentially exploded. And there are a great many people working in this field. There are engineers, physicists, and chemists. And each of these group of people finds something interesting about this family. So if you're a very application-oriented person, these halide perovskites have been shown to be excellent in applications like lasers, photodetectors, LEDs, solar cells, X-ray detectors, gamma ray detectors, MEM resistors, and many other applications. So this is not an exhaustive list of applications. They are good for many other applications as well. Now, if you're a more fundamentally oriented scientist, saying that I'm further away from application, but I'm more interested in the fundamental physics of these materials, they have also interesting properties that are sort of worth studying from the physics perspective. These include high quantum size effects that are demonstrated by large bulk crystals. Some of these metal halide perovskites have very fast and very long charge transfer. The diffusion of charge in these materials are exceptionally long. And then they have high quantum yield light emission and so on and so on. Now, if you're just a chemist like myself, the interesting aspect perhaps in all of this is the solution processability of these materials. So the prototypical perovskite has a formula of ABX3. An example of this perovskite composition is cesium PbI3. Solution processability is an immense advantage of this family for two reasons. A, it allows us to process this at room temperature or near room temperature for, with a low cost. If you compare this to the existing technologies like solar panels based on silicon, at one step, the silicon solar panels are processed at temperatures over 1,400 degrees C. And so there's an obvious advantage of solution processability, but also this solution processability allows us to replace this cesium and lead and iodide with a whole bunch of different kinds of chemical species. And among these chemical species, so I'm going to go into my results. One of the more exciting ones is replacing, for example, cesium plus cation with an organic cation. Now that we can solution process this, we do not have to stay pure inorganic, and we can create what we call hybrid organic inorganic metal halides. And once you go organic, the selection of possible organic molecules is far greater than pure inorganic. And so you essentially, if you're a materials chemist like myself, inorganic materials chemist, you have a large design space to try out great many interesting ideas that you may have learned in basic undergraduate chemistry courses. So from here on, I'm going to talk about some of our exciting results. And we are inorganic materials group, which means that we primarily do synthesis, and we grow crystals like this of new materials and study their crystal structure and photophysical properties. And so among our most interesting materials in the recent 4 or 5 years are these copper halides. If you pay attention, this slide shows a whole bunch of new compounds, with the central being copper halide. And so this is an immense advantage, and these materials are very interesting for multiple reasons. Before we started working on this family, most people in this field were working on lead halides. And people want to stay away from lead because lead is toxic. So even though lead halide materials are very interesting and maybe they will end up in applications, people always have some hesitance with lead because it's toxic. Now, even if you forget about the fact that copper is inexpensive and non-toxic, what we found in all these copper halides is that they have excellent record high light emission efficiencies. This PLQI stands for photoluminescence quantum yield. And these compounds, without any doping or manipulation, have photoluminescence efficiency of almost 100% at room temperature. Now, when I started this project at the University of Oklahoma 5.5 years ago, I didn't believe that any material that hasn't been specifically optimized for it would emit with 100% light emission efficiency. If you're a young chemist or physicist, you can ask many questions here. One of them being, there's something called thermal quenching in light emission materials. That means that if you elevate temperatures, the light emission efficiency typically drops. Why doesn't it apply to these materials would be one fundamental question. Another question you can ask is that we know that solid state materials have what we call defects. This would be vacancies, interstitials, all these other kinds of defects, and they typically harm the light emission efficiency, yet we see 100% efficiency. How does it happen? So these are some of the questions we explore. And one of the interesting things, another interesting things about these materials is that if you pay attention, these are 100% efficient blue emitters. Actually, the development of blue light emitters has lagged behind green and red because blue emission means a very large gap emission. And typically, very large gap materials have this defect states in between that kill the efficiency. But here are like 3-4 new families that were prepared in my lab. So now I will just, in the interest of time, focus on the bottom two. Here are their crystal structures. This you get from doing an experiment called single crystal X-ray diffraction, for which you need single crystals. Now, can you make single crystals of these samples? Yes, very easily so. And this is one of the greatest advantages of metal halides. You can simply dissolve them in polar solvents, and you can grow these rod-shaped crystals in any lab, any part of the world. This does not require a sophisticated setup. This is one of the greatest advantages. You can also make them using high temperature methods, meaning that take cesium chloride or rubidium chloride, potassium chloride, and mix it with copper chloride and heat it in a furnace. You can make powders of them. Now, here are different samples. You see that in this picture, you can see this large rod-shaped crystals. Now, I have to say one thing. If you're working with copper halides, and if you look at this composition, copper's oxidation state in this compound is +1. So I must say that despite the fact that our materials are excellent in light emission efficiency and they're exciting, one potential problem with them is that copper can oxidize to +2 in air. So there are some stability problems. You see that some crystals, if you expose them to the air, you start seeing this development of black spots. These are the samples going bad in real time. With that being said, not all of them are terribly unstable. Some are more unstable than others. So here are the photoluminescence, emission, and excitation spectra. These are typically excited at or below 300 nanometers, and they have photoluminescence emission at about 400 nanometers, and this emission is extremely intense, 100% efficiency. So now if I tabulate the measured properties, a few things are notable here. That first of all, again, 100% light emission efficiency at room temperature, that's great, that's unique, that's very interesting. Another thing that you probably paid attention is that as I'm changing the chemistry of these crystals, you see that I'm going from potassium to rubidium to cesium, or going from chloride to bromide to iodide. It doesn't matter that I'm changing chemistry, the photoluminescence, emission, and excitation peaks stay in the same position. This is a very unusual situation for metal halides, because in metal halides, for many families, we know that if you change the halogen, you change the valence band energy position. Or for molecular people in the audience, you change the HOMO level by changing halogen. Now, if you change the metal, let's say if you change copper, you change the LUMO, lowest unoccupied molecular orbital, or the conduction band. So when we change the chemistry of these different samples, our expectation is that we will change the emission color, emission position of the PLP. But in this family, it doesn't happen, which is a quite unusual characteristic of this family. And we didn't understand why is that the case. Same for photoluminescence excitation, that also doesn't change. And another interesting thing is that the Stokes shifts that you see in this family are large. So what are the reasons for these things? So these are the fundamental studies that we do in my laboratory. Because I was asked to prepare this presentation for undergraduate level, I'm not going to go into very depth of it. But here is band structure calculations that if you're familiar, the audience, people in the audience are familiar, from this band structure calculations, we can extract these plots that are called density of states plots. And if we look at them, this density of states plots tell us what are the HOMO and LUMO orbitals in each of these systems. And what we notice for these copper halides is that HOMOs are made of copper 3D orbitals that are full, and LUMO is made of copper 4s. And that, if we go back, explains the fact that even though you change halogen or alkali metal, the band gap or HOMO-LUMO gap doesn't change, because HOMO-LUMO gap in this family is determined by copper and copper alone, which is a very unique thing, because in lead halides, it isn't like that. In lead halides, if you change chloride, bromide, iodide, you massively change light emission properties. Okay, so we decided that, okay, this efficiencies of these light emitters is excellent. Can we use it somewhere? Here, I'm just briefly summarizing one of our recent publications in this journal down here. You can read the details there. But basically, we wanted to incorporate some of our light emitters into LEDs. In this case, we selected one of our copper halides, which is cesium copper 2I3, and we fabricated a device. First of all, we made a series of thin films. As you know, devices like LEDs and solar panels, these are layered devices, so they have multiple layers. So there's some layer optimization here, information going on in this graphs. I'm not going to go into details, but here's the final optimized device that we made. On one side, we have ITO, which is indium tin oxide. On the other side, we have this electrode. In the middle, we have these layers. But anyway, this optimized device gave us a very good LED with external quantum yield of 7.4%. And this is record high efficiency for lead-free metal halide. So we are currently holding this record. So long story short here, these materials, light emitters that we prepared in our lab, one of their clear applications is in LEDs. But let's look at and compare it to other known blue emitters, these copper halides. And this is from a Nature Materials paper from Ted Sargent's group. And in this paper, there's a table 1, which summarizes key parameters of deep blue emitters. This paper came out before our paper, and if you look at it, these are some of the best known blue emitting materials. And in this, I'm just highlighting with the red box, in the state-of-the-art blue phosphor. This is an europium doped oxide. And even this blue phosphor has lower photoluminescence quantum yield compared to our materials. Our materials have 100%, okay? So we're very happy. But of course, I must admit that our copper halides have their own deficiencies. First, their instability in air. As you can see, copper 1+ can go to copper 2+. And the fact that their excitation is in deep UV, it is 300 nanometer or even higher energy, and the emission is. Now, if you want to use them as phosphors in blue LEDs, blue LED activated phosphors, then we need to shift the excitation energy to the more lower energy region. So anyway, as a chemist, if I'm telling you that we are having a hard time tuning the photoluminescence properties, that is because copper is what is determining HOMO-LUMO, then you're probably thinking, well, why don't you change copper then? And that's exactly what we thought. Why don't we replace copper with silver? And if we do so, then we will change the HOMO-LUMO character. But also, this should help with stability, because silver prefers +1 oxidation state compared to copper. And so it should be more air stable. With these ideas in mind, we prepared a whole bunch of silver halides. And indeed, our idea works. If you look at the band structure, silver halides have quite a different kind of band structure in which now halogen plays an important role, which is exactly what one. And if you look at the emission profiles, they're quite different from copper now. Some of the silver halides are actually almost white light emitters, which is a very interesting thing. Their emission goes from all the way from UV to IR. And so here we asked other bunch of questions. How can a single material emit white light? Meaning white light emission means that this material is emitting all colors of rainbow. How can this happen? And then we did a lot of mechanistic studies, and I'm not going to go into details because this is not the right venue for it. If you have questions, feel free to ask me. But anyway, what about stability? Is stability improved? Indeed, the silver halides are a lot more stable than copper halides. You see that we left them in air for weeks. And unlike copper halides that were sort of going bad within a few days, they are now stable for weeks. And we also heat them in the air at 100 degrees C. Again, they're not going bad. So one of the key advantages of silver halides is that they're a lot more stable. Now, if they're very stable and if they're good light emitters, can we use them in some light emission applications? The answer is yes. Other than LEDs, we can also consider them using for anti-counterfeiting. And so my postdoc, Pawan Kumar, prepared luminescent inks based on this silver halides, and he put it on various kinds of papers, on a black paper, on a white weighing paper. And you can see that these are very durable inks that can be put on just about any surface. He put on different color papers. He put on even polyethylene bag, and he put them in solution, under solution, sonicated them. Long story short, the substitution of copper with silver improves the property a great deal. And now we can make this durable sort of luminescent inks that can be put on anything. And so this is yet another example of application of this metal halide. So this, I think that I may be out of time. Is that right? Yes, it is close to that.
Time is there. You can speak for some more time.
Okay. So, well, I'm coming to the end of it, but in this brief time, I hope I showed you all that. We can prepare these metal halides to be custom design light emitters. These are pictures of different metal halide light emitters prepared in my lab, and these are emission colors at room temperature. So over the past five and a half years, we learned how to make this undoped materials that emit with very high efficiency. But of course, I didn't talk about it too much. We have also compounds in which we have a combination of organic emitter, inorganic emitter in a hybrid organic-inorganic compound, and we can even add dopant. So with these metal halides now, we can, at room temperature, prepare all kinds of materials with customized emission profiles. So for this presentation and for this work, I would like to acknowledge a few people. These are collaborators from Oak Ridge National Laboratory. Mao Du did the DFT calculations, and physicists and chemists here at the University of Oklahoma. And for funding, I would like to thank the United States National Science Foundation, their career program. And of course, my students and postdocs. These are the pictures of my group at different times. I do not have a huge group. Typically, my group size is between 6 and 10, and I have undergraduate student, graduate student, and postdocs. So for this particular presentation that I showed the results today, main contributions were from Tyler Chrisen and Dr. Hariharan Khalil, and also Dr. Aymen Yangbui and Rachel Rokonova. These 4 students and postdocs contributed most to this research. With that, I'd be happy to answer your questions if you have any.
Let me first thank Professor Sapara for delivering an excellent talk culminating different aspects of perovskite halide, highlighting their applications in blue light emitting. With the quantum mill, they could achieve almost close to 100%. It is a very, very important field because, because of the sensitivity of blue light, it is very difficult to design a blue light emitting material with such a high intensity. And then he could also highlighted the fact that he could design different kinds of ink, which can be very helpful for security and anti-counterfeiting applications. Let me thank from all of our INYAS family to Professor Sapara for an excellent talk. And before we end this session, we have few questions from the audience. Let me direct it to Professor Behram. We have first question from Dr. Sriparna. She wanted to know what is the stability of halide with respect to UV and moisture.
So in the case of copper halides, the ones that I showed, I will just go back to so that I can show. Silver halides are stable. So that is my answer. In the case of copper halides, from among all of this, this family is stable under those conditions, but the rest have not very good stability. They go bad in air. They typically end up oxidizing. Copper 1 oxidizes to copper 2+, and they degrade that via that pathway. So if you're exposing it to UV under ambient air, if in the presence of moisture and oxygen, they will start going bad.
We have another questions from Dr. Vinita from BARC. How does the combination of organic and inorganic moiety helps?
So today I just didn't have enough time to go there, but that's a very interesting area because they're both from fundamental and potential applications perspective. So if you put an organic, people are putting organic for different reasons. One reason they may put organic is that you can put a hydrophobic organic molecule such that you improve its water stability. So if you remove, let's say, cesium or potassium or rubidium and put an organic cation that is hydrophobic, that way you can improve stability. This is one reason why you may want to put organic. A second reason you may want to put organic is that organics can be designed to have a HOMO-LUMO gap in the visible region, such that they can also participate in light emission and light absorption processes. If you do that, you can then create a material in which you have a single hybrid material in which you have both organic and inorganic light emitting parts. If you do that, then you end up getting a very, you can design what we call single component white light emitter. Imagine that you have an inorganic part that emits blue, but you put an organic molecule that emits in the yellow red region. If you do that, you can make actually one component white light emitter. And there are many other reasons why you may explore this direction. And so we are exploring this organic, inorganic hybrid copper halides at the moment to improve stability and to also have some control over the light emission properties on the PL properties. So that's a brief answer.
Professor Beram, could you check the photo bleaching property lifetimes of this material?
So lifetimes is another interesting question. In fact, the interesting question here is, what is the emission mechanism could be a question here. And what we call, and I'm not sure if I have time to explain it, but we attribute emission in this material to what we call self-trapped excitons. Now, everyone does that in this field, but then self-trapped excitons are supposed to have a little bit long lifetime. But when I measure photoluminescence lifetime for these different copper halides, they are not all same, they are different. So I want to say that, you know, these ones, some of them are in the nanosecond range, the lifetimes, but some of them are in microsecond range. So there's 1,000 times difference. There are even ones that are approaching millisecond range. And so there's an open question here in terms of why are the lifetimes so different if you're attributing to the same emission mechanism in all of these compounds. And we do not have every and all answers. We're still studying these things here. Photo bleaching, we haven't looked at all.
I will just take one more question. In your band structure, the DFT calculations which you have done, whether the surface functionalities have been taken care of?
Band structures, the calculations are done by our theory collaborator.
Okay.
I'm just going to say that I don't have full knowledge of
that's fine. That's fine. That's fine. And whether you have checked the compatibility of your ink in actual currency note?
No, the ink work was done by my postdoc, Dr. Pawan Kumar, and so I more or less rely on his expertise in this. So this is a new thing for me. My own background is more on LEDs and stuff.
Okay, we could not extend the talk too long because we have another speaker lined up and he has a commitment to his department. So if you have any questions, you can directly WhatsApp me or you can email to Dr. Rajendra. I will convey that to Professor Beram. On behalf of INYAS family, let me thank Professor Beram for an excellent talk. We are indeed grateful to him because it's very, very late night in the Oklahoma, and I'm really very, very grateful to his kind participation on a very short notice. Thank you, Professor Beram. If you want to speak, listen to some of our talk, you can, but I don't want you to be involved in question answer because you have taken most of the question answers. So we'll move to our next speaker for an invited talk, which will be of 15 minutes. Professor Justin Thomas, K.R. Justin Thomas, is a very senior professor and head of chemistry at the Indian Institute of Technology, Roorkee, and he is a recipient of CRSI Bronze Medal and a fellow of Royal Society of Chemistry. His areas of research is organic light emitting diodes, photovoltaics, film transistors, etc. And he will be speaking on tuning triplet harvesting emitters for OLED applications. Over to you, Professor Thomas. Professor Thomas, I'm audible?
Okay, so thank you, Professor Santosh K. Gupta, for giving me an opportunity to give the presentation on this forum. And also, I would like to thank INYAS office bearers for inviting me. And without wasting time, because it's a 15 minutes lecture, I would like directly go into the topic. And considering the audience, I am going to give the very fundamental aspects of tuning organic materials to realize triplet harvesting in organic light emitting diodes. So that is the kind of talk I will be having. So it will be most likely an introductory talk with a lot of fundamentals on the topic and little bit of examples from my own group and other groups which has been published recently. Okay, so actually, before I go to the topic, I would like to give a brief introduction to my group activities. We are concentrating our research on organic materials, whether we use organic materials as sensitizers applied in solar cells or photocatalytic reactions, or emitters in OLED or in sensors as a reporting group. So if you consider organic material, in these two applications, either as sensitizer or emitters, have a kind of opposite level of functioning. So in the sensitizers, light in organic materials absorb the light and then produce electrons. And then when we use the organic material as an emitter in LED, charges are injected into the organic material, and then it leads to the excitation and followed by emission. So our area of research focuses on both of these topics. And I would like to give brief introduction about the LED before I go to the advanced topic which I will be covering in this lecture. So organic light emitting diodes are very simple, sandwich structure, diodes having, triple layer structure in a simplified form, in which you have an anode and cathode. In between that, you have an organic emitter or an organic material, which serves as an emitter as well as a semiconductor. And then if you look at the functional property of the organic light emitting diodes are largely dependent on the characteristics of emitters. And particularly, the following functions are very important, but the transport of charges such as holes and electrons inside the semiconducting layer, particularly inside the emitting layer. And this emitting material which you are using here should have, a primary color emission. In the RGB, primary color, when I talk about primary color, red, green, and blue. And then they should also have sufficient thermal stability, because there will be a lot of heat dissipation taking place during the operation of an LED due to the vibrational relaxation happening in the LED. So you need to have sufficient thermal stability for the organic material that you are using in this device. And recently it has been found that if you are using an organic material in an organic light emitting diode, you will be restricting your LED efficiency to 25% of, that is an internal quantum efficiency will be restricted to 25%. And overall, if you have an external efficiency more than 4%, it means that it is, having a triplet harvesting ability. So having that limitation, now people have been looking at alternatives for using in organic light emitting diodes in the form of emitters, which can harvest singlet and triplet excitons. So thereby you can achieve an internal quantum efficiency as much as 100%. That opens up a way to realize external quantum efficiency higher than 5% in an LED. Okay, so before I go for the topic, I would like to give a brief introduction why organic light emitting organic emitters have a restriction of 25% efficiency cap in LED. So if you look at the way LED is, operating, you have injected, hole and electrons into an organic material, and then it, recombines to produce an excitons. And then this recombination process can statistically lead to, 1 singlet and 3 triplets. So in the way that I have shown here, so the arrangement of the holes and electrons can lead to this kind of 4 arrangements that will lead to 75% of triplets and 25% of singlets. So that is the reason that if you are using an organic material in an LED, they will be able to harvest only the singlet excitons that are produced in this process. So obviously restricting the efficiency of an LED to 20%. And 25%, and then combining with the outcoupling efficiency of 20%, you will be having a maximum efficiency, external quantum efficiency of 5% only. Okay, so that is the drawback. And then those who have studied photochemistry will know that in the fluorescent organic emitters, the problem is because of the intersystem crossing, which is forbidden as per the spin rule. So the organic emitters cannot, traverse from the singlet excited state to the triplet excited state, or vice versa. So in an LED, it is not possible for an organic emitter to harvest triplet excitons in this way. And that is the reason people have been using, phosphorescent emitters, which are all having heavy metals. And in such heavy metals, the intersystem crossing is so fast due to the spin orbit coupling that relaxes the spin rule. So you will be having a facile intersystem crossing in such materials. Thereby, you will be having an internal quantum efficiency for such devices, maximizing to 100%. But now there are problems. This is not a good solution, because you are using an organometallic emitters, which are all having heavy atoms, and they are environmentally hazardous. Due to the cancer and other illness that can happen due to the accumulation of heavy metals in the earth, and they are also very expensive. Besides that, there are also some technological drawbacks with the use of such materials in LED, because they have prolonged emission decay that allows the excited states to undergo several other complicated reactions and then lead to non-radiative relaxation. And there is another problem with the such organometallic emitters is that it is very difficult to realize a deep blue emission. And then, most of these organometallic emitters are, crystalline in nature. So you need to use a host which is having a comparable triplet energy. So that way you are also increasing the cost of fabrication. And as I have already mentioned, that they have a long prolonged emission decay, so there is sufficient time available for the population triplet annihilation, so that will also quench a part of triplets accumulated in an device. So, and overall, above and all, there is a charge transfer process that is happening in most of these organometallic emitters. Or in other words, what I can say is that the excited state will be a kind of charge transfer state. So the emission quantum yield of such materials will be very, very less when compared to the organic emitters, which are having local excitation. So these are the drawbacks for organometallic emitters. So because of this reason, people have focused their attention to organic emitters, but the organic emitters cannot have a intersystem crossing due to the spin forbidden pathway. And then how to make the organic emitters to harvest triplet excitons? So there are, fortunately, we have 3 solutions, which are all not new solutions. They are all known in the textbook for years, but have been exploited for the LED applications recently. 2 of them are originating from delayed fluorescence, and then the third one is a little bit a brand new invention in recent days. Okay, let me give brief introduction about all these 3 solutions one by one. Let me first take the delayed fluorescence that is arising due to the triplet fusion. That is a part of triplet annihilation process. Okay, so I hope that most of you may be knowing the delayed fluorescence, and there are 2 types of delayed fluorescence. One is E-type delayed fluorescence, another is a P-type delayed fluorescence. They are so called because they were all observed first in the Eocene and Pyrene respectively. And then when we talk about this delayed, triplet fusion delayed fluorescence, it is nothing but a P-type delayed fluorescence, which is very common in conjugated molecules having extended, structures. Okay, so in such molecules, you will be seeing a triplet state which is having energy half to that of the singlet excited state. So when such condition is observed, then you can have a triplet annihilation in a very facile way. So you will be losing 50% of the triplet excitons in the form of a singlet ground state during this triplet annihilation. Still you can have a maximum internal quantum efficiency of somewhere around 62.5%. Okay, all that you need here is that the triplet energy of the molecule should be half of the singlet energy, and then you will be seeing that in such molecules, the singlet excited state will be of a local excited state, that is a pi to pi star excited state. So the emission quantum will for such molecules are very high. And then, at any point of time, you will be seeing that, these molecules, since having a, in order to have this kind of, TF-DF in molecules, you need to have a prolonged triplet excited state lifetime. So that is normally achieved by using an extended conjugation in the molecule, which prolongs the excited lifetime for these molecules. Okay, so this kind of phenomenon is observed, as I already mentioned, in the 5 conjugated molecules having anthracene, bifluorine, and in several polyaromatic hydrocarbons. Okay, so I will not talk too much about this one because these are all restricted. This solution is restricted to a class of compounds which are showing a conjugate, high conjugation in the molecule, and then they suffer always due to the solubility. So these kind of molecules cannot be used in LED, which are manufactured by solution processable way. So that is the best way to make LED in the industry. And let me talk about the next solution, that is thermally activated delayed fluorescence. And thermally activated delayed fluorescence first was observed in EOC molecule, so it is also called as an E-type delayed fluorescence. And this is a very common case observed when singlet and triplet excited states are closer in energy, are having an energy difference less than 0.1 electron volt. And there are several organic molecules which are having a delta EST, that is a energy gap between the singlet and triplet states less than 0.1, and such molecules show thermally activated delayed fluorescence. It's so, since the energies are very close, the spin rules are completely overridden, and then you have a facile intersystem crossing due to the fast SOC happening in such molecules. Okay, so this kind of molecules have an excited state which are charge transfer in nature, and then they have also well separated HOMO and LUMO. So in order to find out whether a molecule can have a TADF, you can simply do a theoretical calculation and then see that whether the HOMO and LUMO are well separated. If they are well separated, and then there is a possibility that you can have a TADF. However, this kind of molecules also suffer due to the low fluorescence yield because the excited state involved in such molecules are charge transfer in nature, so they undergo dipole or quenching normally in the excited state. And at the same time, at higher currents, it has been observed that there is more of triplet population, which also lead to triplet annihilation. So the LED efficiency will decrease when you increase the voltage of an operating voltage of an LED, which leads to higher current at the higher voltages. So that is one of the drawback about the TADF. However, these TADF molecules are promising in the sense that one can realize external quantum efficiency as high as 20% in such molecules. In order to have TADF, all that you need is a donor and acceptor structure which can facilitate intramolecular charge transfer. And as I have already mentioned that you need to have a separation of HOMO and LUMO, it can be achieved by 3 different ways. So you can introduce a steady hindrance between a donor and acceptor, so it leads to a tilting, so that donor and acceptors inherit HOMO and LUMO respectively, so you will have a well separation of HOMO and LUMO. And then the second way is to introduce a physical separation between a donor and acceptor, such as a spirolinear wire. You have an sp3 hybridized carbon which acts as an insulator for communication between the donor and acceptor, and thereby restricts the HOMO and LUMO to the donor and acceptor respectively. And then the third option available for realizing TADF in molecule is to introduce cross conjugation. So in cross conjugated molecules, the donor and acceptors are in position in such a way that they are not going to have a direct electronic communication. Donor interacts with the donor fragment rather than with the acceptor. So again, you will be restricting the HOMO and LUMO to the donor and acceptor respectively. So these are some of the design criteria that have been used to make tailor molecules capable of harvesting triplet excitons in a via TAD channel. Okay, so I would like to give one example before proceeding further to the next solution. So in these two molecules, you can see that there is a kind of a cross conjugation. You have an acceptor fragment here and donor fragment here, and then depending on the nature of the donor, they have found that the TADF can be altered in this molecule. So when the donor is slightly weaker, by introducing a carbazole, they could realize a very high TADF channel for this molecule in this series. So when you have a strong donor and a weak acceptor, then the interaction is not so good in the excited state. So you are not having a very good TADF in such molecules. So a compensation is necessary, in which you have to manipulate the donor and acceptor strengths to have a interaction of donor and acceptors in the excited state in a balanced way. So as I have already mentioned, these compounds will all show charge transfer, which can be confirmed by salvatochromism studies. And in the LED, as I have mentioned, that this compound is not having a very good TADF channel, so it is showing an efficiency of 3%, less than 5% within the theoretical limit. And then the other compound, which is having a TADF channel, is showing an efficiency of 9.9%, which is higher than the theoretical limit of 5%, indicates that this molecule is able to harvest the triplet excitons in an LED. Okay, the last solution that I will be talking about is hybridized local charge transfer, which is possible through a hot RIC. So in a TADF, what happens is that the S1 state is coming closer to the T1 state. But in the case of HLCT, you will be having a very high-lying excited, singlet excited state and triplet excited states coming closer to one another. Or in other words, what we can say is that these two states will have similar energy, degenerate in nature. So there is a very facile hot RISC happening or ISC happening in such molecules, and these kind of molecules will have a high-lying charge transfer state and low-lying local excited state. So there will be a hybridization happening because of this between the charge transfer and local excited states, and that can be easily confirmed by salvatochromism studies. So when you are doing salvatochromism, you will be seeing a progressive shift from, when you are going from a non-polar solvent to a polar solvent, you will be seeing a progressive shift in the emission, that when you are plotting via a Lippmann-Mataka plot, you will be able to see a bilinear relationship as it is shown here. So the bilinear relationship will correspond to a non-polar solvent in one region and polar solvent in another region. So in the polar solvent, it will have a very high dipole moment, and in the non-polar solvent, it will have a very small dipole moment. These are all indicative of the fact that in the non-polar solvent, they are having a local excited state stabilized, and in the non-polar solvent, they have a charge transfer state stabilized. So once you identify this molecule is having a HLCT, and then you can also see that impact in the LED efficiency. So I am giving an example that is from the literature. So in this compound, the external quantum efficiency is 3.8%. By changing the triphenylamine donor to a carbazole donor, you are able to modulate the LE and CT states in this molecule and have a very good hybridization between these states. Thereby, you are enhancing the efficiency to 6.95%. And then I would like to also give an example from my own group, which was published in Chemical Communication some time back. And in that also, we have found that when you are using a carbazole and triphenylamine donors, so you have only a local excitation and then leading to an LED efficiency of 2.7%. However, introduction of cyano introduces a charge transfer channel to the molecule. The orthogonality between the LE and CT states introduces a hybridization, and which is confirmed by salvatochromism studies, and then the efficiency is enhanced to 6.5%. Recently, in Angwin Chemie, there was a publication very similar to the compound that we have reported some time back, which is also showing an HLCT and then reported efficiency of 10.8% in an LED. So I think that I have almost coming closer to the end of my talk. With this summary, I will be winding up. I have just demonstrated that there are 3 solutions for realizing organic light emitting diodes, which are capable of harvesting triplet excitons using organic emitters. And these are called as, triplet delayed fluorescence, and, delayed fluorescence involving triplet fusion, and, thermally assisted delayed fluorescence, and hybridization of local and charge transfer excited states. And then we have simply demonstrated that by small structural alterations, you can have a very good LED efficiency, or in other words, by a small structural alterations, you can have huge, functional difference realized in such molecules. I would like to conclude this one with thanks to the funding agencies which are contributing to the work that we are doing in IIT Roorkee on LED, such as CSERB, And I also like to take this time to introduce the Department of Chemistry, IIT Roorkee, and then we are 29 strong faculty group. And then if anyone young faculty members here are interested in joining us, they can, they are welcome. Thank you, Professor Santosh Gupta.
Thank you, sir, for what an excellent talk on covering various aspects of organic light emitting material. You have shown what is how to understand and revise the composition of OLED materials. You have also covered the issues with organic emitting material, and then try to resolve how to organic emitter can harvest triplet excitons by thermally activated delayed fluorescence, triplet fusion delayed fluorescence, and hybridized local charge transformer. So this kind of talk will be extremely useful for optical community who are looking forward to work on organic light emitting material. So I have few questions for you. There is a question from Dr. Rai Chaudhary. Does surface defect affect the emission efficiency and stability? If so, how to address the problem?
Yes, actually, it's a good question. Surface defects obviously will affect the efficiency of an LED. That is an engineering aspect of LED improvement. And that is one of the reasons we always employ organic materials which are having amorphous, propensity. That means that you have a very smooth glass formation, and then, there is no defects or pinholes in the, surface or in the, molecular layer. That is what is very important. So obviously you have to, do trial and error methods to avoid, pinholes or defects in the structure. And then many of the times, it's all avoided by using blending the materials which are capable of giving very smooth, structures, surface structures. Okay, so that is an engineering aspect. As an organic chemist, we are not much interested about that one, but, it can be solved very simple, blending methods and others.
Sir, there is a question from Dr. Praveen Kumar. How you see the future of organic transparent LEDs?
Yeah, already there is a lot of progress, as there is a lot of progress happening on the solar cells also. When we talk about, these kind of materials, and you need, absorption capability and emitting capability and everything. And then when we talk about transparent materials and their use in, LEDs, obviously you need materials which can absorb very less visible light, but, shows light emission in the visible region. So such molecules should have a, very large Stokes shifts. That is what one can expect. So I hope that, research in these directions are also going on. So I think sooner or, that I'm not much sure about the progress made in that area, but, all that you need is a material which is having a large Stokes shift to be employed in such materials, so that you can have a very good, transparency in the visible region.
I have personally few questions for you, sir. So how you because of a lot of presence of carbon, hydrogen, and lighter atoms in organic compound, the non-radiative phenomena will be very prevalent. But how you compare the existence of organic phosphor in coming year over inorganic phosphor? Because efficiency wise, I see there is a lot of issues with organic LEDs in compared to inorganic one.
Yeah, as you said that, the thermal vibration of organic materials due to rotations and other things, there are several rotable groups in organic materials. That is one of the drawbacks. And then obviously, that will also lead to the reduction in the efficiency, and then long-term stability is another issue because of the thermal vibrations, that the molecules may be thermally degradable. So that is another issue also. However, recent progress showing that, introducing several, heavy atoms such as chlorines and bromines can, lead to, phosphors, room temperature phosphors. There are work, and then rigidity is another aspect people have been addressing. So there have been several compounds which are having, rigid structures such as bicarbosols have been found to have room temperature phosphorescence. So rigidity can resolve partially the, concern that you have raised. So that will have lesser kind of thermal vibrations or, thermal degradations in that way. So recent work based on boron-based molecules, which are very rigid, polycyclic aromatic compounds incorporating boron centers, have been found to have very good, thermal stability as well as, TADF for the time being. It is possible that in the future we will be able to have a very good, phosphorus based on organic matter. So everything depends on the directions of research. I hope that, it may take some time because it is not so robust as inorganic phosphorus.
Sir, just one last comment I would like to hear from you. How you see the future in this direction on making composites of inorganic and organic phosphor, and whether any kind of doping can improve the existing problem in organic compounds?
Yeah, I hope that may be a very good way to improve the efficiency. But the problem of energy transfer, you see that always there will be energy transfer that will be happening. So in many times it may so happen because of the energetics, organic materials will serve as a host for inorganic, materials. So thereby, the inorganic materials will dominate, in the functional property of an LED or the, the composite that you are using. So that need to be addressed also. Probably I think that by judicious choice of inorganic and organic materials, we will be able to have a composite which can, balance the properties, in the outcome.
Thank you, sir, for such an excellent talk and a very intensive discussion. If any question will be there, I'll personally email you and discuss with the question raiser. Sir, on my personal behalf and on behalf of my entire INYAS community and family, we render you a very sincere thanks. And once we really appreciate your time and effort in making the excellent talk for all the listeners. Thank you, sir. Thank you so much.
Thank you very much. Thank you very much.
Before any further ado, I would like to invite our next speaker, who is my colleague and a senior scientist at Bhabha Atomic Research Center, and she's also an associate professor at HBNI. Dr. Vinita Grover has an expertise on structural property relationships in complex oxide material for an application in the area of novel ionic conductors and lead-free ferroelectrics for energy conversion. She has been awarded a lot of awards, and some of the notable among them are DI Young Scientist Award and the Young Scientist Award by Indian Nuclear Science Society. She is also a fellow of Maharashtra Academy of Science. I would like to invite Dr. Grover Gupta to deliver her talk. Dr. Gupta.
Thank you, Santosh. Thank you very much for these generous words. And a very warm good morning to all of you. It is indeed a pleasure being with you here today. So in the next 15 minutes, I would like to give a glimpse of how the luminescent material can be used for bio applications. How, not always for lighting. We can see we can look out for other applications for luminescent material. Okay, so far, all of us know what luminescence is. If a material is capable of emitting light, so if we excite it under some sort of external excitation, it will go to the excited state and emit light of lower energy than what was provided to it. So this is the energy of the emission is always lesser than the energy of excitation, and we call it fluorescence, we call it luminescence, we also call it down conversion in certain technical terms. Okay. Now, depending on how you're exciting your material, basically, you're exciting it by electrons, you're exciting it by current, mechanical force, heat, it takes different names. In this particular next 15 minutes today, what we will talk about is photoluminescence. That is when you use electromagnetic rays, that is UV, visible and IR, or the chemical reaction to excite the molecule to get the luminescence. Okay, so when we hear the word luminescence, it strikes light in our mind and it takes us to the lighting technologies. Okay, and which is very important, I must admit, efficient renewable alternatives of lighting are definitely going to contribute to the sustainable development goals. But there are very many applications, the other uses that luminescence can be put to and has been put to very good extent. be it the high-end applications for sensors for space exploration, the fiber optic communication, security application, Dr. Sepirov talked about it, then nanothermometry. And what we will concentrate today is I would want to give you a glimpse of bio applications. Okay. So now when I talk about bio applications of luminescence, what am I referring to? That is imaging, first and foremost, therapy, that is treatment, then studying the molecular interactions at cellular level using luminescence, and then quantification of biomolecules, which is also called bioassay. Okay. This is, I must point here that we talk of interdisciplinary science, but this is one particular field which is truly at the interface of chemistry, biology, and material science. So what is the concept? How it is done when I talk about bio application? Basically, what we take is we take the luminescent probe, the material which will actually give out luminescence, modify it appropriately so that it goes where you want it to go in the cells. It is taken up by the cells and tissues. And when you excite it with the appropriate wavelength, it will give you the luminescence, and that luminescence, that emission will give you useful information about what is happening under the sample, in the sample that you want to investigate. And bioluminescence, A, non-invasive, simple, you're shining light, minimum perturbation, no damage to the healthy tissue. You can actually monitor what is happening on the real time, and you have access to the molecular processes happening in cell, which you cannot access by other probes. And of course, the fact that there is availability of highly sensitive detector system makes this modality of optical imaging very feasible. And multimodal strategy, I'll talk about it in a minute. Okay, so luminescence probes, when we are talking about the imaging technique, what we need is the probes, the material that can show fluorescence. What are the different kind of probes that are used for bio applications? They are organic dyes and fluorescent proteins. Dr. Justin was talking about some of the organic molecules. Quantum dots, these are few nanometer particle size, and inorganic nanoparticle, mostly based on rare earth elements such as europium, terbium, ytterbium, arnium. These are the ions that actually absorb and emit the light. So criteria for the probes, obviously, they have to have good brightness. After all, you need it for imaging. They have to have biological safety, non-toxic. They should be photostable. They should not get damaged under light, and good sensing ability. And of course, the energy level should be in the range where we want them to absorb and emit. All of these probes, be it organic, quantum dots, inorganic, they have their pros and cons, and we use them depending on our applications. So coming to the first application, bioimaging. Bioimaging, as the word says, is employing luminescence for imaging the biological system. So what is done here is you basically take your luminescence probe and then administer it to cells. If you are doing it in vitro, that is outside the living body, or in the petri dish, if in vivo, suppose let's say in mice. And then what happens is cells take them up, and if they're taken up nicely, then when you shine light on them, then depending on their energy level, they will give you the light, and they'll tell you where the cells are, where the tumor is, what is the size of the tumor, or the cellular processes that you're trying to understand. Now, this is just one example of how the luminescent lipid particles were synthesized in the labs, specifically for cancer cell imaging. The lipid particles were synthesized by, I won't go into a lot of details, though this is what we do as chemists. Lipid particles were synthesized by a microemulsion based process. Then they were coated with an organic dye, and the figure shows here, the B is the figure where the cancer cells were administered these particles, and A is the figure when you shine light on them and they show fluorescence. C is merging them, and then you can see clearly that light is coming from the cells. Okay, so that means they were taken up, means the particles were really amenable for bio applications. Now, not just that, an important thing with these luminescent nanoparticles is that you can use it for multimodal imaging. Now, what is that? Multimodal means that I incorporate two or more kind of imaging modalities. To make it simple, suppose I have nanoparticle which I have developed for luminescent application. Now, I also introduce a component that is magnetic. I can use this for optical imaging. I can use this for MRI. The concept is that each technique has its own advantages and shortcomings. And if I use them in conjunction, it will help the clinical practitioners to locate the things nicely and make a better judgment. This is one example that I took from one of the publications. In this photograph, you can see the gray areas. Those are basically the organelles that were marked by MRI. Now, when a probe was used, which are dual modality, that is optical as well as magnetic, you see now, not only you can mark the boundaries in a better way, but this intensity of color actually shows the concentration of those particles, which means the concentration of the cancer cells. So better imaging, better judgment, better treatment is what these things aim at. Okay, this is one example of how we actually synthesize the dual modality nanoparticle. If you see the formula that is written on the left-hand side, it is Fe3O4. Fe3O4 is magnetic. It is modified so that, we can do some chemical jugglery on it. YPO4EU is luminescent, again modified with amine. Now they are made to undergo a reaction where they form an amide linkage, and the single nanoparticle has both Fe3O4, YPO4EU, and can show both the magnetic response and the imaging capability. Okay, these are some studies that were done, and I won't go into the details since I'm only talking about the concepts here. That was imaging. How can the luminescence use for therapeutic application? Just one example, which is given the name photodynamic therapy. So what it means is that the drug that contains the luminescent particle, the light absorbing particle, are either applied or administered orally. And when the light is shown on them, they get excited. And the excited state reacts with oxygen to form something that we call as ROS, or reactive oxygen species. Now, this reactive oxygen species are very reactive. They attack the tumor cells, react with their biomolecules and destroy them. And this leads to tumor destruction. That was how therapy done. Okay. Now, I also mentioned that we can use luminescence for biomolecular interaction. Just a glimpse of how the concept of how this is done. Suppose I want to study, there are two proteins A and B, and I want to study whether they interact in a particular biomolecular process that I'm monitoring. So what we do is, I tag protein A with a dye I call donor, tag protein with a dye I called acceptor. Interesting thing is that energy levels of donor and acceptor are such that where the donor emits, the acceptor takes the energy and gets excited. So if your two proteins who are tagged with this are interacting with each other, and in that you are exciting at the energy that belongs to donor, but you get the emission from acceptor, means energy transfer is happening. And that will happen only when the two proteins are at the distance of 10 nanometer or less. That means they are interacting. And it also depends on how those proteins are structurally oriented towards each other. So basically, this is a very good modality to understand the protein interaction, the biomolecular interaction in your system that you're investigating. One thing that I would like to point your attention towards is, when we use the UV visible based optical imaging, there is a problem. What happens is the biomolecules in the living organism, they themselves absorb in this range. So what happens is you get a lot of background luminescence from these biomolecules as well, which is undesired. And because of this, there is a very, the tissue penetration of your exciting radiation is very small. So these two are the hindrances. What are the solutions I can look for? Of course, I can excite it at lower energy, let's say NIR. It will have better penetration and lesser background. But suppose I want to see the emission invisible. What will I do? There is a concept that is called upconversion. In fluorescence, what happened? One photon taken in, one photon of lower energy given out. Upconversion, what happens? Two photons of lower energy are taken in, and one photon of higher energy, visible range, is given out. So I can see the emitted light. This is like you give 250 paisa coin and you get back 1 rupee coin. This is what upconversion is all about. Okay. So this is just an example of how fluoride nanoparticles were synthesized in our lab, doped with ytterbium and erbium, and how they showed you give an NIR excitation of 980 nanometer, which does not show in visible region, but you get two colored photons, and how the light can be tuned by varying the size of the particles. Okay. Solution 2. The problem was with UV visible excitation. What if I excite the nanoparticle even before injecting in the living organism? There comes the class of the material, which we identify as persistent luminescence phosphors. Persistent, as the name suggests, that here in these materials, the luminescence will persist even after the source is turned off. An example is zinc gallate manganese nanophosphor. They were synthesized. And as you can see in the schematics, that they were irradiated with UV even before injecting. And then they were injected in the mice where the tumor was. And it was observed that a luminescence and imaging could be done up to 6 hours after the excitation were done. And fortunately, these nanoparticles did not show any toxicity as well. Third concept and the last concept. What if I don't excite it with light? If there is no need to excite it with light, but I need to have an excitation modality. In that case, scientists took the inspiration from bioluminescence. That is, the excitation source now is not light, but is a chemical reaction. All of us know what bioluminescence is. All of us have been enchanted with fireflies when we were kids. So what happens there is a chemical reaction happens. In these organisms, they have an enzyme that is called luciferase, and they have a chemical that is called luciferin. Now, this luciferin, in presence of luciferase, reacts with oxygen to give something which is called oxyluciferin in excited state. And this oxyluciferin comes to the ground state, emit light, and which is what we observe. So if I want to use this, what I need is the enzyme luciferase and the chemical luciferin. So how the scientists have used this? Suppose I want to study the growth of the tumor in the mice. So what they do is they take the tumor cells and do the genetic engineering so that they encode these cells with the genes, and those genes can instruct the formation of luciferase enzyme. Okay, now they have the enzyme in their body, and the tumors are injected in the mice, incubated for some time. And when I want to study now how does the tumor looks, I will take luciferin, add to it. Luciferase is already present. It will give luminescence, and I can image it. So whenever I want to image it at regular interference, I can keep adding luciferin, and a real-time in vivo image of the tract cell can be obtained. I want to test the efficacy of the drug which has been developed. After you have injected the tumor cell, incubate it, and then add the drug, and now monitor over the time. So you can see whether the tumor is shrinking or growing. So basically, you're not exciting it at all. So the background signal is minimum. Okay, and there are many other uses, quantification of proteins, cell population, bacterial cell population, and all can be done using this concept. Broad comparison, I will not go into the detail. Earlier we studied fluorescence, now we studied bioluminescence, that is chemical process basically. Fluorescence is high intensity, you're giving so many photons, so it is a brighter image. But bioluminescence, even though it is a low, it's not that bright, the advantage is background is virtually absent and it is highly biocompatible. Okay, so just coming to the end, when I was reading about it, there are two interesting offbeat manifestation of this process that I saw. Scientists are now working on actually genetically engineering the plants. This is an example of a tobacco plant that you see here. So you actually do the genetic engineering so that luciferase and luciferin, or let's say only luciferase is expressed in these plants, and then you can get the glowing plant, and they might serve the applications such as street lighting with less energy consumption and all. Sounds very futuristic, but yeah, there are startups that are working on that. Then lamps based on bioluminescent bacteria to decorate homes. And third and very last and very interesting thing that I read about is there is this artist called Hunter Cole. He uses the bioluminescent bacteria and make drawings with it and then transfer it to the Petri dish. Now it is a living thing, so it will die within few weeks, but it gives nice painting kind of thing. And over the weeks, as it dies, it brings about different aspects of the art. So yeah, it is fun. In the end, I would say is that healthcare for all is one of the important sustainable development goals of United Nations. And chemiluminescence for bio applications is going to play a big, huge role in this. And with this, I would thank INYAS for this wonderful platform, Dr. Santosh Gupta for this opportunity, and I thank you all for your patience. Thank you.
Thank you, Dr. Vinita. What an excellent, excellent talk. Let me tell you, our colleague from INYAS has been praising a lot of good thing about your talk. And we have seen a wonderful talk from Dr. Vinita Grover, who has covered different aspects of how luminescence can be of great helped for bioimaging and therapeutic applications, and he's also shown the aspect how a chemistry and physics can be culminated for this. She has shown how to synthesize application dependent material, luminescent material, then covering the advantage of dual modality in cancer imaging, how the role of Foster's resonance energy transfer can be helpful in achieving brighter aspects of bioimaging and cancer imaging. She could also touch upon the fundamental aspects of upconversion, downconversion, photoluminescence, persistent luminescence. Then she took an example of a great persistent luminescent material, spinal gene galette, and she could show some of the applications. She really covered an excellent variety of things in her talk. Let me thank you from all of us at INYAS for such a wonderful talk. See, for three of us, yourself, myself, and Neha, will take up the question in a different session of 20 minutes. So over to you, Neha.
Thank you, Santosh. So I'm here to actually introduce Santosh ji itself. So Dr. Santosh Gupta is serving as a scientific officer at Radiochemistry Division in BARC, and as an assistant professor of chemical sciences at Homi Bhabha National Institute, Mumbai. His area of research encompasses photoradioluminescence of lanthanides and actinides, and he works on defect spectroscopy, upconversion of nanoparticles, optical materials for health, energy, and environment. Dr. Gupta is the recipient of several notable awards, among which are Fulbright and JSPS Fellowship, DAE Young Scientist Award, Scientific India Young Scientist Award, Fulbright OLF SMC Bronze Medal, Tarun Datta Young Scientist Award by IANCAS. He's been inducted as a member of INYAS just this year, and he has been doing his part quite well, and he's chairing this session. So he'll be introducing us to the power of UV light in the context of the recent pandemic and the water technology. Santosh ji, the dais is all yours. Santosh ji, you are muted.
Thank you, Neha, for those kind words. Let me start my talk. I'll be the brighter aspects of fluorescence, luminescence, and other thing has been covered excellent by Dr. Saparov, Dr. Justin Thomas, and Dr. Grover. So one of the gray area of photoluminescence is UV light emission, which becomes extremely important in the context of current scenario the whole world is facing, that is COVID surge, and the problem of rural area where water is one of the main problem. So I will show how UV light can be of great help in resolving this problem. The key benefits of using light for any application is that they are benign, no involvement of any chemical, and with the advent of LED, it is extremely affordable, extremely bright, extremely powerful, and its efficacy for germicidal things is very, very fast, and it gets triggered in a second. And the microbial cell does not develop resistance to this technology, and they are proven to be work very effective against bacteria, mold, fungi, and even viruses. Just a slide that all the molecules are at thermal equilibrium under room temperature. Unless you excite it, once you push them with certain external stimuli, they'll go to a high energy state. They'll sit there depending upon their lifetime, and once their lifetime is over, they will decay down. And if the decay is between the same state of the same spin multiplicity, it is called fluorescence. And if there is certain kind of phenomena which is triggering intersystem processing, we get a delayed fluorescence that is called phosphorescence. So this is the Jablonski diagram. Entire photophysics of material depends upon this phenomena. As Dr. Vinita has told, depending upon the mode of excitation, we have a variety of phenomena in the domain of luminescence. We have photoluminescence. If it is excited by electron beam, it is cathodoluminescence. If it is excited by ionizing radiation, very intense ionizing radiation like alpha, beta, gamma, which from our perspective in BRC, it becomes very important for development of scintillator and all. Radioluminescence, from LED perspective, if your material gets excited by electric field and it emits light, it becomes great important implications for solving the lighting problem of rural technology. Thermoluminescence, if you can store the light, store the energy and then reheat it, there is a development of trapping and retrapping, and you get a light emission. You have a chemiluminescence. If under the influence of ultrasound, you get a sonoluminescence, pressure, triboluminescence, and if chemiluminescence is happening in some biological process, it is called bioluminescence. I will not go upon the example which Dr. Vinita has covered, that is the role of luciferin in bioluminescence by fireflies. There is another protein in jellyfish that is called aquarin. But this kind of luminescence is of great implication in current scenario in understanding the failure of certain big civil construction like bridges and all. If you have a triboluminescent material which can sense the stress, it will give you an indication much before the actual failure of the material. Radioluminescence for night security, signal storage, security application. You have a liquid tritium molecule. If it can be coupled with a bright phosphor, there is no safety problem. It has a very long lifetime. It has a very low energy beta. It can resolve the variety of problem. Chemiluminescence, it can be a great thing. There is one example, but if luminol can be combined with perovskite, it gives a very bright luminescence. And then electroluminescence I spoke about. Up conversion, go from low energy to high energy, that is called up conversion. You go from high energy to low energy, that is called down conversion. Persistent luminescence, you keep on exciting the material, all the energy will go to an excited state, it will keep depositing in the trap, and once you stop the excitation, depending upon the trap depth, trap density, it will come and recombine with the luminophore and it will give you the ions. What is so special about ultraviolet light? We don't bother about ultraviolet light. Everybody's wearing ultraviolet glasses in going outside because it is lethal for human being. In ultraviolet light domain, we have three different types. One is called UVA light, that is between 315 to 400 nanometer, UVB between 280 to 315, and UVC between 100 to 280. You see, sunlight emits all these three types of radiations. UVB is not absorbed by ozone layer, and it can be lethal for our skin and cause melanomas, which is one of the type of skin cancer. B, majority can be absorbed by the ozone layer, but some still get into our body and it can cause skin cancer. But we are very safe from UVC because ozone layer is there to protect us and it will not enter our human body because it is very, very lethal. If UVC gets into our body, it can destroy our DNA and it leads to a death of the human being. Why? What is so special about these three? Because of their wavelength range is such that UV ray penetrates much deeper layer of the skin. You see UV layer penetrating into much deeper layer. UVB, much shorter wavelength, can get into intermediate stage, but UVC getting absorbed by ozone layer is not of much harm. But then the entire world is looking into the importance of UVC, how to produce this light. The UVC is found to a boon for viral inactivation. You know, UV light produces electromagnetic energy that can cause certain kind of photochemical reaction in nucleic acid. Every body has nucleic acid, either it can be DNA or RNA. What it does, it triggers the formation of certain kinds of dimer. If it is DNA nucleic acid, there is a formation of cytosine and thymine dimer, and if it is RNA nucleic acid, there is a formation of uracil dimer. If these kinds are happening, then what you can do, all the virus, bacteria, pathogens available in the atmosphere, which is creating a hell lot of problem to the global society, a lot of problems can be solved. You see the day-to-day wider impacts of UVC in the broader industrial community. It is used for surface sterilization, air sterilization, static water sterilization, flowing water sterilization, food industry. You go to any restaurant, they have a UVC lamp, sterilizing. They do it before a human being enter. That is the problem. I will just discuss sterilization lighting, horticulture lighting, to protect the crop from these pathogens, and then phototherapy. Under the aegis of Atmanirbhar Bharat, our DIE itself has developed Neel Bhasmi, which uses a single wavelength of 254 nanometer UV lamp, and it was found to inactivate the novel coronavirus as well as other microorganisms. Then where is the problem? Why we cannot have that UVC lamp and we get freed of this nonsense which is happening throughout the world? You see, there have been UVC lamp installed in the hospital. There are UVC lamp installed in the transport. But the problem is that you cannot use these UV lamps when human beings are present, because as I discussed, this UV lamp can destruct human being in a variety of ways. They can lead to skin cancer, they can lead to eye cancer, another eye problems, because I told you they leads to damage of DNA or RNA, and that can have a severe impact on human body right from top to bottom, whether it's the skin or eye and other problems. But there is a light at the end of the tunnel. We are worried about UVC. It can solve the problem, but not in the presence of a human being. There is a Professor Charlie Ironside who is at Perth at Curtin University of Australia. What he found that a certain portion of UVC light, that is called far UVC, from 200 to 222 nanometer is considered safe for human being. You see, the conventional UVC, it penetrates and damages your skin. You see, far UVC, it will touches only the surface of the any surface or any things where you are trying to explore it. So what he told, if such LEDs could be mass manufactured with this sweet spot, that is far UVC, they can be integrated into everyday lighting and we can get control of this pandemic. Sterilization could become very easy, very effective, and we could control any kind of new infection. It could flatten the curve and without having any problem of social distancing, and there should not be lockdown. You see, UVC was such a nuisance. You come down from that domain to 200 to 222, you can solve the variety of problems. He further projected UVC is fine at killing the bacteria, but it's lethal to human being. But far UVC can kill the bacteria, but it cannot penetrate into our skin. There are several hypotheses working over the globe. A lot of discussion is going on, and there are few things which came out. David J. Brenner and his colleague found on their experiment over a mice that are exposing mice to 222 nanometer light from a krypton chlorine excimer lamp. There was no damage to skin. They could but successfully kill the superbug. The same group performed the experiment with 220 nanometer light on a H1N1 influenza. They found they could inactivate 95% of such viruses without any destruction to human skin. The other group from Japan, Sachiku Kaidazu and his colleague, they found it is safe to the eyes, no damage to the corneas of rat exposed to 222 nanometer electromagnetic radiation. So, being a shorter wavelength than other UVC light, far UVC photons are barely able to penetrate the skin's outermost layer, which is often tens of micron thick. On the other hand, it can still penetrate bacteria and viruses, which are usually less than 1 micrometer thick. So future belongs to far UVC. You can incorporate such UVC lamp, far UVC lamp in surgical theater. You see, if you have such lamp, people can still work and you are free from those pathogens, bacteria, viruses. In hospitality industry, you put this UVC LED lamp, people can keep working, and those who are taking their food in the restaurant or anywhere, they are calmly enjoying those food and those delicacies without much of problems. School and colleges, kids have been stored in their houses for last 2 years. If we can have such LED, safe to human, inducted in the school, colleges, we can get rid of this problem and all those transport facilities. Big impact. If such excimer lamp 222 nanometer can be inculcated in spaces such as hospitals, school, train and buses, we can help the people without risking them. Such viruses like COVID-19 can be taken care of without practicing social distancing. But what is the issue? With the example, Excimer 222 lamp, the only issue is that it is bulkier in size, shape, and weight, so it is immobile. It can work very well when it is stationary. What is the way out? The way out, if we can design a far UVC light LED, compact, movable, scalable, there can be a revolution in such a phenomena where we can have personal protection for all the people who are working. But you know, one LED can be converted into another LED, as it can be seen in our commercial white phosphor, thanks to these three gentlemen who got Nobel Prize in 2014 for invention of gallium nitride single crystal, which when combined with cerium yellow phosphor, we get a white light. With this analogy, 1 + 1 can make 2, 2 + 1 can make 3. Then why LEDs cannot be manufactured to emit at almost any wavelength by adjusting the alloys which are currently existing? Gallium nitride, 3.4 EV, gives the light emission at 360 nanometer. Aluminum nitride, band gap of 6.4 EV, gives UVC at 210 nanometer. Why we cannot mix them? There were papers in electrochemistry, communication, and nano nature that they have synthesized aluminum gallium nitride LEDs with perfect emission of 222 nanometer and aluminum nitride with emission of 210 nanometer. But the problem is that they could not achieve the desired quantum efficiency. The quantum efficiency was found to be very few, only few percent, but we need for commercial efficacy 20 to 40%. So there are a lot of scope for young generation to take up this important problem, to help the society, to help every country, to help the young people in designing new short UVC LED with desired quantum efficiency. With advent of such, everyone mobile phone will have such LED, and we can have virus-free society. Just few minutes. Such UVC light can be of great implication in water technology also. Currently, use of chlorine and other stuff is so difficult, so dangerous for human being. But with UVC light, we can have very sustainable and efficient solution to this problem of water, which is persisting in a huge domain in the rural area. How can we take care of that? If we can synthesize a material which can absorb a solar light, which has a wide range from far UV to NIR, we absorb visible, and if such phosphor material can give UVC, that is called NIR to visible upconversion or visible to UV upconversion, we can inactivate such virus present in water. A Kate Settle group from Clemson University have done a lot of work in this area. Somebody can see that how they have converted X-ray into UVC, NIR into UVV, visible into UVP, and if we have such phosphor, you put into your water, absorb the sunlight, that phosphor will absorb the sunlight, it will give away the UVC light, it will hit on your water, and you are free of those bacteria. We have done some work on this direction, but by doping, we have done synthesis of nanostructured material, we have doped gadolinium, thulium, and ytterbium, and what we have found, we would achieve UVC, but for water purification technology, but we are far from achieving far UVC emission. We believe this I try to cover a general aspect for entire research community, how intense discussion needs to be put into the picture of designing a science toward optical community among designing far UVC light, which can, because the pandemics will keep on coming, but research has to be sustainable in direction which will be helpful and boon to society. I would like to thank Dr. Pujari, my director at Radiochemistry and Isotope Group, Dr. Mahapatra, my division head, Dr. Acharya, our section head, and all the divisional and sectional colleagues at DRC, and my INYAS family and CC member for giving this opportunity. I could not have started my INYAS journey better than this, being a session chair and being a speaker. And all the researchers who have been working in this extremely challenging area and making available scientifically enriching data for carrying out future research on similar direction. Thank you, one and all.
Thank you, Santosh ji, for such a wonderful talk. It was amazing to hear about UV B, A, and C, and how the far UVC can be used in this particular important case of pandemic, and also for giving us some future inspiration on the usage of such light for water purification systems. Thank you very much. We'll take the questions, I think, in the end. Right?
Yes. We'll take the question. It's a separate session. Our next speaker, Dr. Neha Shardana. She was a friend of mine for a long time, and she's also my colleague at INYAS. Dr. Neha, just a brief introduction of her. Dr. Neha is an assistant professor at IIT Roper. She has been a PhD candidate at Max Planck Research School. Her areas of expertise is on site property, relationships of material for high temperature applications, and plasmon-based material and metamaterials for optical sensing devices in visible and IR regime. She is an active member of INYAS, and she will be speaking on plasmonics and metamaterials towards futuristic application. Over to you, Neha.
Thank you, Santoshji. I hope I'm audible. And I will be taking a little bit different route than just luminescence. I'll just expand a little bit into the field of plasmonics and metamaterials. So when we have light, usually when we talk about light or any kind of light from the whole electromagnetic spectrum, whether it be visible eye or whether we go to higher frequencies like terahertz or gigahertz, or we go to lower frequencies like the UV or X-rays, we talk about the whole spectrum in this talk. So please be sure that I'll be talking about this whole spectrum. So when we want to talk about all these things, we first should know that there's plenty of room at the bottom. That means if I talk about gigahertz, if I talk about UV vis, or if I talk about X-rays, I need to talk about structure sizes or materials in the specific range or in the specific dimensions. So what actually are plasmons? Plasmons are collective electronic oscillations. And what do you mean by collective oscillations is they have a coupled state between an elementary exciton and a photon. There is a light matter interaction. So there are basically three kinds of plasmons. There are propagating surface plasmons, usually on flat, thin films. There are localized surface plasmons if you have nanoparticles which are arranged in a certain fashion or a random fashion. And there are bulk plasmons if you have very thick films. So why do we need these plasmons? Usually when we talk about light, it usually creates problem when we want to go beyond the diffraction limit of light. So a possible way is to convert light into plasmons. So you can have shorter wavelengths than the incoming wavelength of light. So is this a new thing that we are talking about? Well, no, this has been known for many, many centuries. It was not known, the name, the plasmons was not given, the word nanotechnology or nanoscience was not given to it, but it was known, and the artisans of 4th century AD made this very nice Lycurgus cup, which if you see under reflected light, you see a green color, but under transmitted light, you see red color. And these are nothing but gold nanoparticles which are embedded in this particular glass tint. If you have ever visited, say, a church, supposedly in Goa or somewhere else, you can see these beautiful tinted paintings which have red, green, blue colors. And these are all nanoparticles made up of silver or gold. And the thing that you are seeing here is actually a plasmon, a gold plasmon at the metal dielectric interface. The dielectric here is glass and the metal here is gold or silver. And originally, the first noted thing, which is this beginning of the scientific thing, was actually the gold nanoparticles, which were made by Michael Faraday in around 1857, and they are still very stable, these pink and red color things. So these are showing the plasmonic red color. So usually when we think about gold, we think about gold as having a golden or a yellow color, but just by tuning the size of the gold particles, the size of the gold nanoparticles, we can tune the color from red, blue, green, depending upon the size of the same. So why is it so important? We want to replace the slow electronic devices to fast photonic devices. And of course, we are going towards a future where we talk about quantum computing as well. So we are somewhere before quantum computing in this case. And usually the speeds of photonics and the size of electronics are quite dependent. So if you remember the Moore's law, it says the number of transistors on a chip doubles every year. And that can be taken into effect, the efficiency and the speeds of data transport over long distances if we have much smaller size of elements and the speed increases while the heat losses and the other problems can be reduced. So that is why nanoscale data storage is actually limited due to the interconnect delay times, and this interconnections between the optical part and the transistor part, this can be bridged if we can bring plasmonics and metamaterials as the bridging gap to it. Plasmonics has a wide range of applications. Vinita ma'am has talked already about targeting and imaging of different tumor cells and how these cells can be eliminated. She used different kinds of photoreceptors, and the similar thing is used for plasmonic nanoparticles here, which are sensitive to the incoming wavelength of light. Furthermore, we can make certain arrays. We can make cloaking devices where we can hide a certain wavelength of light or a certain background. We can generate plasmonic hotspots, which are the basis of surface enhanced Raman spectroscopy. There are many other applications like biosensors, spacers, that is surface plasmon lasers, and nano antenna arrays, which are actually paving the way for the next generation of antenna and communication. So after the introduction to plasmonics, I would like to introduce metamaterials. So we know if something moves, it's biology. If something stops, it's physics. If something stinks, it's chemistry. And if something doesn't work, it's engineering. And surely everything, if they bring together, then it is meta and it is beyond our conception. So metamaterials are basically, they are materials which have been designed by humans to go beyond the normal interactions in mechanical, acoustic, or optical domains. I myself am a metallurgist. So by that definition, I'm very happy I'm making metamaterials for a long time, right? So by definition, a man-made synthetic composite material with a structure such that it exhibits properties which are not found in nature. We have been making it at the brass and the bronze age itself, because we were converting from iron oxide to pig iron and to steels these days. So we are already metamaterial scientists and we are working on this. Well, I would say no to this. And I would say the metamaterial definition has changed a bit over the period of time. So metamaterials are, of course, they are artificial periodic structures, and they have lattice constants that are much smaller than the wavelength of the incident radiation. So mind you, it can be used anywhere from the X-ray to your far infrared radio waves and so on. So the important characteristic here is they have a negative refractive index characteristic. So what does this mean, the negative refractive index characteristic? So if you look at this graph, on the x-axis, we have the epsilon, the dielectric constant, and on the y-axis, we have mu or permittivity. And if both these values, epsilon and mu, are positive, these are for dielectrics like glass, it can be air. So these both are positive. So these are known as dielectric positive materials, and they have a forward propagating wave of the electromagnetic spectrum. Then we have materials which have epsilon greater than 0 and mu less than 0. They are called as mu negative materials like iron, cobalt, etc. And they have an evanescent decaying wave that goes down with time. And similarly, if we look at the second quadrant here, then we have an epsilon which is less than 0 and mu which is greater than 0. And these are the epsilon negative materials. And these are metals like gold, silver, which are such good plasmonic materials. So all these three, in the first quadrant, in the second quadrant, and the fourth quadrant are existing in nature, or somehow we have managed to make them with very less of effect and chemical synthesis that we are able to make these. But these materials in the third quadrant with epsilon less than 0 and mu less than 0, dielectric negative materials, they are not found in nature, and they have a backward propagating wave. So how do we make them? So if we have a mu negative material like these split ring resonators and an epsilon negative material with these rod structure, and we bring these two together, what we get is an metamaterial or the DNG materials. And let me just revise this, that properties of these particular materials are dependent on the external structuring of the material rather than the composition or the material properties itself. So the light matter interaction is very important here as well. And the periodicities and the structuring is the key factor for the metamaterials. So when we talk about this whole regime of the electromagnetic rays, that is from the X-rays to the long radio waves, so we can have structures which work for long radio waves. We can have structures which can work for microwave. We can have structures which work for the UV rays, depending upon the structure size. So if we have structure sizes in centimeter range, they will work for radio waves. If we have something in few nanometers, then they will work in the IR and the visible range. And similarly, we'll have to go below that range if we want them to work in the X-ray regime. And this is actually a breakthrough when we want cloaking of certain materials. So what is cloaking? So if we have a source of light and we want to see from the left side, the light, the material here in blue is the metamaterial, which bends light in certain fashion, so that the bending light still reaches the observer, and the observer does not know that there was something here in this orange color over here. So we are cloaking this orange using the blue metamaterial. So the Harry Potter's invisibility and the bionic eye of the Terminator, can this be reality soon? Well, the Harry Potter's invisibility was in the visible regime because it was transparent to the human eye. And the bionic eye, of course, it is already today we can see people working on it and testing these bionic eyes. So this has been possible because of the metamaterials and the structuring of the various lenses, which help focusing the light onto the retina. When we talk about metamaterials, they can be optical, they can be acoustic, and they can be mechanical. They are of interest to the physicists, to the chemists, to the electrical engineers, to the mechanical engineers, because of their wide possibility of their various possibilities of different properties, like their negative Poisson ratio, their negative elasticity, their absorbance frequencies, their transmission along a certain particular wavelength of light, else they will not work. They can work as switches and so on. So what are the applications of this metamaterials? Of course, the invisibility cloaks, which I was talking about. Then they can be stealth paints and on the fighter jets. Of course, this has been used. The stealth paints are being used because these are much easier to produce because the structure sizes that we are talking about are in few centimeters. So these are easily possible. But when we are talking about the invisibility in the visible range, which is around 400 to 750 nanometers, then we will have to talk about structure sizes around 100 to 150 nanometers, which need photolithography, e-beam lithography, or nano imprint lithography kind of techniques to be fabricated. These metamaterials, once they come into commercialization, they will be able to give us see-through gloves for surgeons, so they can easily have surgeries without having the hindrance of their hands in between the surgery part and their devices in their hands. It will take away the blind spots for the drivers in the cars when we turn sometimes left or right. Sometimes we are not able to see the bikers or a pedestrian who is walking on the street because of the blind spots in our cars. Of course, bionic eye, night vision glasses are already the current applications which the metamaterials are being used. We are also making highly efficient and compact satellite antennas with metamaterial structures. So as I said, the Moore's law says the number of transistors in a dense integrated circuit, they double every 2 years. So to solve that thing, we need to miniaturize different things. We need to increase the speed of communication. And that is why plasmonics and metamaterials have come hand to hand, where we have gold, silver kind of plasmonic materials, which are being structured with the help of metamaterial structuring, And they both, when brought together, they increased the speeds of transmission. And of course, what they did is they reduced the heat losses a lot. So the lot of transmission of data has a lot of loss in it due to heat, due to any external reasons, and this reduces all these problems as well. So the miniaturization of bulk antennas from these big Yagi Uda antennas that were in our childhood, when we used to have our TV sets and we used to go on the top floor and play with the antenna made up of aluminum. The designs are quite similar, but now they are as small as the one held in this person's hand, and they are flat. So they don't have to be three-dimensional at that particular dimension of an antenna. So if you have seen the upcoming of the antennas, you can see we started with this Yagi Uda antennas, then we went to big dish, and now we have a small box that is working as an antenna. Our mobile phones also have antennas, and you don't have a Yagi Uda antenna standing in front of it. So the future is we'll be having much smaller antennas and much easily accessible antennas in the future. So these metamaterials are being used even in the space exploration programs for various kinds of sensors. So here what you are seeing, this is a Mars soil that is being tested using metamaterial and plasmonic based antenna, a chemical sensor, of course. Then other things are the structuring is very important in antennas. So certain antennas are being used to put it on your teeth so that you can track what you eat. If you have had too much of sweet today, so you should stop. So they tell you these, and they are easily integrated with a smartphone and an app. And another nice thing is some people are using these antennas as devices for dentures, which are misplaced regularly, and you can just find them using an app. So these kind of antennas can be used for keychains, and means they have immense applications if you want to find the applications for such metamaterial structuring antennas. Our group works on various structures of antennas. We simulate them, and we also use experimental data to tune the different kinds of antennas in the various electromagnetic regimes, whether it be terahertz, whether it be gigahertz, and so on. Plasmonics and metamaterials are being used for increasing the efficiency of solar cells, because if you talk about a flat solar cell, lot of light is directly reflected back into the atmosphere and lost and not coming into the solar cell. So for that, you can structure the solar cells in different ways, like a zigzag fashion or a rose fashion or a checkerboard fashion, and that increases the conversion of the incoming light into the solar cell itself, and that increases the efficiency of the solar cell. So currently we are going through the SARS-CoV-2 pandemic, and as you know that the diameter is around 100 nanometers. So here we are trying to have very fast detection possibilities. We had RT-PCR, we had rapid antigen, rapid antibody tests that are prevalent. But it would be really good if I can have a small liquid kind of a thing, and if I can just take a sample from my nose or my saliva and put it, and I can see a color change, whether red, orange, red to orange, or green, orange, or some other colors. That would be really good. It would be very fast, and I can see it from my eye. So people have been working since the start of the pandemic, and they are using aggregated gold nanoparticles, which are capped by certain moieties for their plasmon, for enhancing their plasmonic response. And these particular gold nanoparticles, they change color from blue to purple depending upon whether you are SARS-CoV-2 positive or negative. So people are also using portable Raman for already detecting influenza and rhinovirus. And the substrates which are being used in these portable Raman are plasmonic metamaterials. And this will be the future when we talk about detection and day-to-day life will be the substrates for these kind of sensing mechanisms. So with this, I would like to thank the INYAS family and Santosh ji for inviting me for this talk. And thank you so much for your kind attention.
Thank you, Neha, for an excellent talk, giving culmination of plasmonics and metamaterials and introducing the subject very well to the audience and how plasmonic can be important for fast photonic devices. Then the different kinds of metamaterials you explained and how both can be of great help for miniaturization technology. Then you discussed about your work from your lab on graphene-based metamaterials. And some example you touched upon related to testing of Mars soil and how the important role a nanoparticle can play for detection of COVID viruses. So on behalf of my personal note and from all the INYAS family, I really thank you a lot for giving us such an excellent talk and for being acceptance to my invitation for the same. Thank you.
Thank you.
The session is open for discussion. If you have some questions, you can put it in the chat box. I will ask directly to the speakers like myself, Dr. Vinita, Dr. Neha. For one of my questions, Dr. Pooja, I believe, has asked, what about the generation of ozone under UVC? Yes, indeed, it is of great concern, but there are work going on development of soft glasses which allow lights beyond 210 nanometer, and it cut down absolutely 184 nanometer light, and in more or less way we can control the generation of ozone. Dr. Kutub has asked, Santosh, please work on that direction and make a safe far UVC light. Kutub is a very, very dear friend of mine and a Fulbright fellow. I assure you, Kutub, I have already started working on that direction, and with certain collaboration here and in with foreign friends' help, I'll be able to do some work very soon in that direction. Anyone would like to ask any question, any comments? I personally feel the session was excellent. We have covered the wide spectrum. So see, the entire light technology is based on electromagnetic spectrum from UV to infrared, X-ray, and whatever. So we have touched upon UV, visible, NIR, up conversion, down conversion. Dr. Behram covered how important the halide perovskite will be in future optoelectronics, and he see how it can make a scalable, tunable light with very high quantum efficiency, touching upon blue light with quantum efficiency of 100%. And then Dr. Justin Thomas say how the future belongs to a very flexible, scalable substrate based on organic light emitting material. And he told me how to resolve the issue pertaining to the intersystem crossing and increasing the efficiency of phosphorescence. Dr. Vinita gave an excellent overview of how luminescent material can be of excellent addition in resolving the problem pertaining to fluoroimmunoassay, bioimaging, therapeutic purposes, and etc. I try to give a brief of how UVC and work on UVC of great impact for future generation on resolving this kind of pandemics. Neha touched upon a very beautiful fundamental aspects of plasmonics and metamaterial and how they can be of great help from fundamental to an advanced application, touching upon various optoelectronics and resolving biotechnology, medical application, etc.
Dr. Santosh, I think there are some questions in the chat box, and I think there are people raising the hands.
Yes.
Santosh, can I
also
ask?
put in the WhatsApp group.
Can I ask the question, Santosh?
Yes, madam, please go ahead.
Yeah, first of all, congratulations for excellent session coordinated. So my question about ozone was like most of the product you see for the disinfection, they are based on 254 nanometer.
Right, madam, mercury. Yes.
So, and you said that 184 is the one which is responsible for the ozone production. So it means that 254 is not the responsible for ozone production because there are a lot of concern about the product based on 254.
See, I'm telling you, the major culprit is 184 nanometer light, because beyond 184 nanometer light, generation of ozone is very drastic, and that's why the people have started working on air. There should be an air outlet to take out of the ozone, or there should be soft glasses which transmit only light beyond 220 or 210 and completely cut down 184. Yeah, there are concerns which you rightly said, but still it's a gray area. A lot of work needs to be done on resolving the issue pertaining to ozone.
Okay, maybe I'll contact you separately.
Yes.
We are working on this. So thank you.
Thank you, ma'am. There is a many thanks to
Santosh. I put few questions in the WhatsApp group. You can take directly from there. It will be easy for you.
Sir, are you focusing on the material innovation aspects of Dr. Praveen has asked me, are you focusing on the materials innovation aspects of UVC? Dr. Praveen, particularly I am working on converting near infrared and visible light into UVC. So I am working on designing a nanophosphor luminescent material where we excite the material with near infrared light and visible light. We will be tune the several synthesis parameter, defect engineering, doping engineering, so that we could efficiently produce UVC light. As far as far UVC light is concerned, I have not done any work on that aspect, but yeah, soon I'll be trying to do certain collaboration on that aspect and see how we can go how far. And there are questions, Neha, how the viral genotype can specified using metamaterials. To you, Neha, Dr. Rohini has asked how the viral genotype can specified using metamaterials. And what is the difference? And one more question, Neha, what is difference in surface plasmons for thin and thick films? Two questions to you, Neha.
Okay, Rohini ji, the viral genotype cannot be specified using a metamaterial. It's just the sensitivity of the Raman equipment that is increased and enhanced using a metamaterial kind of periodicity. And of course, you have to use your own linkers between the metamaterial and the viral genotype. That linkers need to be good enough so that the material enhancement can be used for this particular specified genotype. So it's nothing to do with the genotype detection or their sensitivity. It's about increasing the spectroscopic sensitivity. And Rajendra ji, the surface plasmon for thin and thick films, of course, if the thickness is much higher, like bulk materials, then when we talk about the evanescent wave in the thin films, you can have resonance with the reflection from a bottom side, whereas in the thick, you do not have that reflection. The evanescent wave, it dies down. So that is the only difference that that I can think about.
Thank you, Neha.
Anything?
I think Kutub is raising hand.
Yes, Kutub.
Hi, Kutub. Hi, Santosh. Wonderful.
Hi, Kutub. How are you?
Yeah, so, my question is, you said that far UVC has a range of 200 to 222 nanometer.
Yes.
And as I understood from your presentation, that people are trying to achieve the production of 222 nanometer UVC.
Yeah,
so why not there is in this range, means 200 to that 22?
See, Kutub, that's why they have done experiment with the range is 200 to 220. Right now, the commercially available lamp with 229 nanometer is that Krypton lamp, that is Excimer lamp, which so lot of the experiment which have been done pertaining to the same with mice or rat or whatever experiment they have done with 222. But now recently what they have done, they have tried to combine like gallium nitride, aluminum gallium nitride to make a LED kind of laser. So they have achieved 210 as well and 222 nanometer as well. But still, Kutub, it's a very, very immature technology. Lots of work needs to be done.
Yeah. Okay. Wonderful. Great start, Santosh. Congratulations.
Thank you, man.
Okay, I think we are done with the technical session. I really thank Santosh for nicely coordinating and organizing this very interesting talk. I think we have covered a lot of things and which are related to society. We should benefit society by our research. This is very, very important. I also thank all the speakers, keynote speaker, invited speakers for covering very important aspects of this theme. With this, let's conclude this session, and I all request all of the members to join our INYAS general session at 3 p.m. So please join 5 or 10 minutes before. Thank you. Thank you all.
Thank you, Rajan.
Bye-bye.